Hi everyone. In this video I'm going to demonstrate multiple indicator, multiple cause models using the AMOS program. These models are also referred to as mimic models. And before we get started, I want to mention that underneath the video description you will find a link to a PowerPoint, and that PowerPoint contains information that you might find helpful as we go through the presentation. The PowerPoint also includes links to the SPSS data files that I'm working from, as well as links to the AMOS files that I'm going to be covering. So I'm going to assume that you already know how to use AMOS in order to draw out your models. Now, before we get started with our demonstration, let's cover just a few reasons why you might consider using a mimic model. So first off, you might use this type of model to test whether one or more manifest variables predict variation in a latent construct with multiple reflective indicators. And this is actually going to be example 1 in this presentation. Secondly, you could use mimic modeling to assess the possibility for differential item functioning, and that will also be an example in this presentation, basically our example 2. You could extend the mimic model and with respect to the differential item functioning and identify potential factors that may explain the presence of differential item functioning. So that was actually covered in an article by Cheng et al. From 2016. And then you might use mimic modeling to assess validity concerns related to formative indicators. So for our first demonstration, this is the model that we're going to be testing. And this was originally described by Jorskog and Sorbum in 1996 in their Lisserl reference guide. The analysis is based on data from interviews from a sample of 530 women and this is described by Hodge and Tryman in their 1968 article. The model was also tested by Schumacher and Lomax, where they reanalyzed the data using the Lisserl simplest language. So we're going to be using AMOS in this presentation, and just briefly, the variables included are income, occupation, and education, and church attendance, memberships, and friends seen. Those are all the manifest variables, and then we have this social participation latent variable in the model. So you can see at the top, basically Schumacher and Lomax referred to this portion of the model as the measurement portion, and that's because you have the church attendance, memberships, and friends seen serving as our manifest indicators of the latent social participation factor. And then down below you can see that we have the structural portion of the model where income, occupation, and education are predicting social participation. Now for this demonstration we're going to be using this data set right here. You can see the link that I've given. Again, this is in the PowerPoint. And you can see that we have correlations among our variables as well as the sample sizes, and then down below we have standard deviations. So in the original article by Hodge and Tryman, and also then picked up by Jorskog and Sorbum, only correlations were provided for the information related to our variables. So there were no standard deviations given, so we can't if we were just analyzing the correlation matrix, then we wouldn't be able to obtain unstandardized estimates as we would if we had standard deviations available. So what I did in this particular demonstration was just to kind of go a little bit further, and I just put some standard deviations in here. These were not from the article or anything. These are just some numbers that I put in to make this a little bit more realistic. So at any rate, here's our model once again, and this is the link to the data to that AMOS file if you want to download it to run the analysis. But I'm going to go ahead and open up AMOS and run the analysis. So here we have our model, and if you go under the data files right here, you'll see this is the data file that we're working with. Again, that was what was linked in the PowerPoint presentation. Just so you know, in terms of the analysis properties, things I've requested, obviously we're sticking with the default maximum likelihood estimation, and under output I've selected standardized estimates and squared multiple correlations. I'll go ahead and click on Calculate Estimates, and we get our output. So I'll click this button right here, and you can see that we have right here we have the unstandardized estimates in our model, and then we have the standardized estimates. If we go back to the unstandardized estimates, I do want to mention that this coefficient right here of 1, this is because I had fixed that factor loading to 1. So if we go back, there it is right there, and the reason why is to achieve identifiability for the model. So so at any rate, that's why that's there, but the remaining estimates are just that, they're estimates based on our data. And I'll go ahead and click too on standardized estimates, so you can see that here the double-headed arrows are containing the correlations among our exogenous variables, and then the remaining coefficients in the structural portion are essentially our path coefficients, and then in the measurement portion of the model, these would essentially be analogous to correlations between each of our indicator variables and the latent factor. So we'll go under the text file right here and take a look at the model fit, and you can see that right here we have the chi-square goodness of fit test. It's close, not quite significant at the conventional 0.05 level. Just keep in mind that historically a significant chi-square value would indicate that the model is not fitting the data well, but we generally don't rely solely on the chi-square test to evaluate goodness of fit. We also look at other fit indices, mainly because the chi-square goodness of fit test is impacted by sample size, and given that SEM is a large sample procedure, it's not unsurprising to have situations where you have a significant chi-square test, but then other indices indicating that the fit is actually good. So we'll look at the GFI and AGFI. Basically with these indices, values 0.90 or above would be considered indicative of an acceptable fitting model. Obviously, as we get closer to 1, the better the fit. The same goes for our TLI and CFI right there. So you can see right there that the model is exhibiting good fit. When we look at the RMSEA, a value of 0.05 or below is taken as an indicator of close fit. Values up to 0.08 would be considered acceptable fit, and you can see right here that we are in the close fit category for our model. When we click on estimates right here, you can see our measurement portion and our structural portion. These are the unstandardized coefficients right here. So these are the estimates. So for the measurement portion of the model, you can see our 1, where we fix that factor loading to 1, and then we have our unstandardized factor loadings right there. Both of those are statistically significant. Then we have income in our structural portion, income predicting the social participation. It's a positive and statistically significant predictor. We have education predicting social participation. It's a positive and significant predictor. With respect to occupation predicting social participation, it's a positive. The coefficient is positive, but it's not statistically significant at the conventional 0.05 level. So obviously we can scroll down. You can see that we get the standardized coefficients, basically the standardized factor loadings and the standardized coefficients for the structural portion in the model. You can see I've kind of scrolled down a little bit further. You can see the correlations among the exogenous variables given, as well as the squared multiple correlations that are given. Within the measurement portion, the squared multiple correlations are essentially the communality estimates, whereas in the structural portion is the standard R-square. So the R-square for social participation is 0.258, and it indicates that those predictors accounted for about 25.8% of the variation in the social participation variable. Okay, so for our second example, we're going to test this mimic model by Brown, and we're not going through every step that he provided, but in this particular model we have two latent factors. We have social phobia and agoraphobia, and there are 6 indicators of those factors. So the first 3 indicators are for social phobia. The remaining 3 indicators are for agoraphobia, and you can see that for each case, one of those factor loadings is fixed at 1 to identify the model. You can also see too that we have disturbance terms associated with each of these 2 factors, and that's because we're using this variable sex right here as predictors of those 2 factors. So this variable right here is obviously a manifest variable, and it's a binary variable that is coded 0 for identified female and 1 for identified as male. And in addition, we have sex predicting variation in this A3 indicator. And so the basic idea in this case is that what we want to do is we want to test whether there are sex differences or gender differences with respect to A3 after we control for the latent factor agoraphobia. And if we find that there is a difference, then what that would tell us is that we have evidence of differential item functioning with respect to the A3 variable. So in other words, it's not just a construct variation that is accounting for how people respond to the item, but also whether it could be that there are gender or sex differences with respect to the response. So here we have just a screenshot of the SPSS file that I've set up, and again you can go to this link to download it to run the model. So you can see right here I've got correlations among the items, basically S1 all the way to A3, and then we have the variable sex included, and then obviously we have the sample sizes and the standard deviations. Okay, so here we have our model opened up in AMOS. Again, if we go under the data view, this is the data set that you can download at that link from the PowerPoint. And I think I've just kind of gone ahead and discussed the general characteristics of this model. One other thing too is that you can see right here that there was the addition of a correlated disturbance between the latent variables for social phobia and agoraphobia. So let's go ahead and run the analysis. I'm going to go ahead and I'm sticking with pretty much the same options that I went with before, and we'll go ahead and run the analysis and click on this button right here. And under the unstandardized estimates, you can see that the path from sex to this social phobia variable has a negative unstandardized coefficient. It's negative 0.11, whereas the path from sex to agoraphobia has a coefficient of negative 0.48. So given the coding of the sex variable, basically 0 for identified female and 1 as identified male, you can see that those persons that were identified as male would have scored lower on agoraphobia and potentially on social phobia than those identified as female. And then when we look at the coefficient for sex in relation to A3, the unstandardized coefficient is negative 0.98. Again, that would indicate that persons identified as male would be scoring lower on this variable than, or this indicator, than persons identified as female. So let's go ahead and go into our output file right here, and we'll go to model fit, and the model fit was quite good. You can see that we have this chi-square goodness of fit test is non-significant. You can see the GFI and AGFI and the TLI and CFI, all of those are indicating quite good fit of the model to the data. When we look at the RMSEA, it's actually 0 or thereabouts, which is indicating a well-fitting model. When we look at the estimates right here, now we can perform or look at the significance test related to our question. So you can see in this case we've got, again, we have the ones right here are reflecting those fixed factor loadings. The remaining factor loadings within the measurement portion of the model, all of those are statistically significant. when we look at the relationship between sex and social phobia, the coefficient is negative, as we saw before, but it's not statistically significant. So that would indicate then that that individuals identified as male were not significantly lower with respect to the latent mean on social phobia than persons identified as female. On the other hand, when we look at the sex agoraphobia relationship, you can see that we have a negative coefficient and we have significance. So it appears that persons identified as male did score lower on the latent mean for agoraphobia than persons identified as female. And then when we look at sex in relation to the A3 variable, we have the same sort of situation where basically persons who are male scored lower on average than persons identified as female, and this is controlling for the agoraphobia latent factor. So that gives us some indication that we have differential item functioning with respect to the A3 variable. Finally, as I mentioned before, in the PowerPoint you'll find on the last page references and further reading, so be sure to check that out. So that concludes this video demonstration, and I appreciate you watching.